Today we're going to talk about one of the particular topics in section 2.4, which is Chebyshev's theorem. Now, in one of our other sessions, we talked about the empirical rule, and I want to go over that real quick because Chebyshev's theorem works kind of like the empirical rule. So the first thing I'm going to do is share with you, remind you about the empirical rule that states if a data distribution is bell-shaped, then this is similar to the picture that we had in the other session about the empirical rule. With bell-shaped distributions, you see the mean is in the middle, and you can see that 68% of the data values will fall within one standard deviation, 95% of the data values will fall within two standard deviations, and 99.7% of the data values will fall within three standard deviations. So that's just a reminder about that. And so today what we're going to talk about is, well, what if the data distribution is not bell-shaped? Or what if we have no idea what it's shaped like? Well, then we can't use empirical rule. But we might still be interested in at least estimating the percentage of data values that will fall within a certain number of standard deviations from the mean. And so what we have that we can use for any data distribution, no matter what it's shaped like, is Chebyshev's theorem. So first I'm going to show you the definition of Chebyshev's theorem, and then we're going to look at some examples. So this is, This is the definition of Chebyshev's theorem. So it's under a measure of variation because it has to do with standard deviation and the mean. And notice the first thing that's here is that it may be applied to data distributions of any shape. So you aren't restricted to bell-shaped distributions. And the second thing, and this is important, it says it is used to estimate the minimum percentage of a data set that will lie within k standard deviations of the mean of the data set. Now, a couple of important words there. Notice it says it's used to estimate the minimum percentage of a data set, and that will lie within k standard deviations of the mean of that data set. So, and that number k, you can do that. K can be anything, but it has to be bigger than 1. And so what we're going to look at, I've kind of rewritten Chebyshev's theorem up here for you. And we're going to look at how we can apply this to some specific examples. So what Chebyshev's theorem says is that at least, and that gives us a formula for this. So we're going to get a formula right here. And that formula is 1 minus 1 over k squared. And then we're going to multiply that by 100. And that will change it from a fraction to a percent. Okay, so this is the formula that we're going to use to find that minimum percentage. Notice this says at least. That means it could be more, but it's going to be at least this percentage. Now, you see this k right here. That number k in the formula is how many standard deviations you're talking about from the mean. So, and notice that k has to be greater than 1. So it can't even be equal to 1. It could be 1.1, it could be that. It could be, so it doesn't have to be a whole number, 1.2 and so forth. Up to, you really wouldn't get much bigger than 3, because even in irregularly shaped data, all the data is generally going to be within 3 standard deviations of the mean, unless they're very unusual. very unusual things. So what I want to show you is I'm going to give you a couple of examples of how this works. So let's pick a number bigger than 1 that's pretty easy to do. Let's say within k equals 2 standard deviations. And so let's find that minimum percent of the data values that would be within 2 standard deviations. And notice I don't have to know anything except how many standard deviations I want to be within from the mean. So I don't have to know the mean. I don't have to know the standard deviation. This is just going to give me the minimum percent that's within the number of standard deviations of the mean, whatever those things happen to be. We'll look at a particular example from the homework in a little bit. So if k is 2, then using this formula up here, we're going to have 1 minus 1 over k squared, and then we'll multiply it by 100 so that that will give us a percent. So our k in this case is 2, because we want to know what's the smallest percentage that would be within 2 standard deviations of the mean. So we would have 1 minus 1 over 2 squared times 100. Also, I'm trying to show you how your work should look. And this gives me 1 minus 1/4 times 100. When you do 1 minus 1/4, you're going to get 3/4. You can also do this as a decimal. So you could do 1 minus 0.25. But if I do it this way, and you can do it either way, you can change 3/4 to a decimal. So if you did 3/4 as a decimal, 3 divided by 4, you would get 0.75. And then when I multiply that by 100, that would give me 75%. Or if I want to look at it this way, if I just multiply 3 over 4 times 100 over 1, I get 300 over 4, and that would also be 75%. So no matter which way I look at it, if I want to know the minimum percentage that will be within 2 standard deviations of the mean, that will be 75%. So you could make a chart over here. You could say, okay, so if k equals 2, at least 75%. So we did k equals 2. Okay, let's try a different one. Let's let k equal 3. So I'm going to change this number right here. So that's going to change this number. And of course, it's going to change the answer. So for this next one, I'm figuring out what is the smallest percentage or the minimum percentage that will be within 3 standard deviations of the mean for any data set. So now I'm doing k equals 3. So let's do k equals 3. So if I do that, if k equals 3, then I come here, and where I see the k in the formula, I'm going to put a 3. And then 3 squared is 3 times 3, which is 9. And then 1 minus 1/9, that's 9/9 minus 1/9. And that would be 8/9. And it might be helpful to you on this one to change 8/9 to a decimal. If you change 8/9 to a decimal, 8/9 as a decimal, do 8 divided by 9, and that's going to give you 0.8, and it's going to repeat. It's going to go forever. 0.888 repeating. So then we have, if we wanted to multiply that by 100, then that's going to move the decimal point over 2 places. And that would be the percent, and they would tell you what they want you to round to. So let's suppose we were going to round to the nearest 1/10 of a percent. Then we might change that. Here's the 10th place. we wanted to round it to the nearest tenth of a percent, then because that next number after the tenth place is 5 or bigger, we round this up, and that would be 88.9%. Now, that number does not have to be a whole number. That number can be a decimal. So it could be 1.5. If you wanted to know how many data values or what percentage of the data values will be within 1.5 standard deviations of the mean. So I'll do one more of these and then we'll look at an example that's in your homework. Okay, so if k is 1.5, then from our formula up here, we would have 1 minus 1 over 1.5 squared, and then we'd multiply it times 100 to get that changed to a decimal. And I don't have my regular calculator, so I'm going to use my phone for calculator. And if I do 1.5 squared, 1.5 times 1.5 is one way to do it. So this would give me 1 minus 1 over 2.25. And then I'd have 1 minus, and I'm going to use parentheses. And I got 0.555 repeating. And then that's going to be multiplied by 100. So this gave me that. And I'm going to double check that to make sure it's true. So in my calculator again, I'm going to do 1 minus parentheses 1 divided by 2.25 in the parentheses equals 0.5 repeating. And so I'm convinced that that is the correct number. Now multiplying it by 100 is going to move the decimal point to the right 2 places. So it would end up being 55.55 repeating. And since I multiplied by 100, this is now a percent. Okay, and if I wanted to round, so I did k equal 1.5. And what I got for the minimum or the at least percent was 55 point. If I wanted to round to the nearest tenth, that number in the hundreds place is 5 or bigger, so I'd round this up and it would be 55.6%. And so what we just found out is for any data distribution, at least 75% of the data values are within 2 standard deviations. At least 88.9% are within 3 standard deviations, and at least 55.6% are within 1.5 standard deviations. So I'm going to leave those up here, and we're going to look at an example problem that you're going to have in your homework. So I'm going to look at it. I'm going to put it up here. Here's an example problem from your homework. And while I'm reading this to you, I'm going to write the important information on the board. This says, from a sample with n equal 36, remember lowercase n is the sample size, so it's a sample of size 36, says the mean duration of a geyser's eruptions is 3.43 minutes. Since this is a sample, the mean would be x bar, and it says is 3.43 minutes. And the standard deviation, so for standard deviation of a sample, that's little s, is 0.55 minutes. And the question is, it says, using Chebyshev's theorem, determine at least how many of the eruptions lasted between, how many will be between 2.33 and 4.53 minutes. That's the question. Between 2.33, and notice it says at least. Now the reason why it says at least is because that's what Chebyshev's theorem gives you. It gives you an at least, and it gives you an at least percentage. Notice this one doesn't say at least what percent. This says at least how many. So we're going to have to use Chebyshev's theorem first to find the percent, because that's what it gives us. And then we'll see if we can use that percentage to figure out how many of these 36 eruptions in a sample would last between 2.33 and 4.53 minutes. So let's go back to what Chebyshev's theorem says. Remember, it gave us this formula that gives us an at least percentage. But to use that formula, we have to know what K is. And K is the number of standard deviations from the mean. And they want this. They didn't give us the number of standard deviations. All they said is they wanted it between 2.33 and 4.53 minutes. So somehow I've got to figure out how far those numbers are from the mean. So I'm going to draw a number line. Now I'm not going to draw a bell-shaped distribution because I don't know what the distribution is shaped like. They didn't tell me that. But I do know if I put the mean here in the middle, which was 3.43, and I'm just going to add a standard deviation on either side, add and subtract like we did with the empirical rule. So first I'm going to go within one standard deviation. So standard deviation was 0.55. And so I am going to take the mean, 3.43, and add 0.55. And that gives me 3.98. And I'm going to add 0.55 again. So that's plus 1 standard deviation. If I add 0.55 again, I get 4.53. Ooh. Notice that's this number here. And I got that by adding 2 standard deviations. So possibly our K is 2, but let's double check. Let's go backwards 2 standard deviations from the mean and see if that lands on this 2.33. So if I go back 1, so I'm going back to the 3.43 and I'm going to subtract 0.55. That gives me 2.88. So that's minus 1 standard deviation. And then if I subtract another 0.55, I get 2.33. Well, that worked out nice. So this number is minus 2, and this one's plus 2 standard deviations. Sorry, it's a little messy. So that means what we're really saying is that we want K to be 2. Okay? Now, we've already done K equal 2. We already know the minimum percentage. I wrote some of these up here. So let's look over there. When we did K equal 2, sorry, they don't line up better. When we did K equal 2, we got that the minimum percentage, at least 75%, will be within 2 standard deviations for any data set. So we know if K is 2, it's going to be at least 75%. So we know that. We sort of know the answer to the question. We know what percentage. But the question wasn't what percent is within 2 standard deviations. The question was how many? How many? So how many out of what? We'll go back to the top. That's where this sample size comes in. They told you in this sample 36 eruptions that they timed total. Okay, so what we're going to look for is 75% of that sample size of 36. Now the math you do to find a percentage of something, and this is a very important thing in statistics, is you first write the percent as a decimal, so that's 0.75. The word of in math almost always means multiply. So we're going to multiply that times 36. So I'm going to do 0.75 times 36, and that gives me 27. 27, that's 75% of the 36 in the sample. 27 of them would last between 2.33 and 4.53 minutes, according to Chebyshev's theorem. Now, it could be more. Remember, Chebyshev's theorem gives you a minimum. So it could be more than 27, but you could expect at least 27 of the 36 to be between these two time frames. So that's an example of one that you're going to have that's a little bit harder. One of the ones you're going to have has a little bit easier numbers, but I did the harder one so that it wouldn't throw you. The easy one will seem really easy then. These are towards the end of the 2.4 assignment. So that's an example, and that's what Chebyshev's theorem is used for, is to find the minimum percentage of data values that are within a certain number of standard deviations of the mean of the data. And hopefully you won't have any trouble now doing those last few problems in section 2.4.